Hello everyone, welcome to another video lecture. On this lecture we will discuss the topic Maxima Minima, which is an application of derivative, and this is the last topic we are going to discuss on derivatives. Well, to understand this Maxima Minima, I would like to start with few examples first. We'll see what is actually Maxima Minima graphically, then we will see how to deal with it mathematically, and we will solve few problems on that on the same topic. Okay, so here I have first, okay, let me consider few functions, that is over here, number 1, number 2 and number 3. These are all simple function I have tried to collect. That is, all these three functions, the algebraic functions, no sine, no cos, no trigonometric, no log, nothing is there. These are all simple functions. Now if you wish to visualize this function, that means if you want to plot the graph of the function will look something like this, for this, and for this. Well, let me tell you one thing, these are not just random graphs I have plotted. This is a real-time graph, that is, this graph exactly represent the given or the function which we have on the left hand side. That is, I have used some mathematical programming to plot the graph. So these are exact representation of graph. Now what do I mean by maxima minima for this function, like maxima minima of this, maxima minima of this, and so on. Now from the graph it is understood this particular point and this particular point for the first graph. Within this graph, this is the highest height that graph will attain and this is the lowest height that graph will attain. So definitely this particular height is maximum value and this particular height is minimum value. And what about maxima minima? Now this height is corresponding to this particular point on x-axis. So we call this point as point of maxima, and this particular height, which is minimum, is corresponding to this particular point on x-axis. So we call this point as minima. So what is our goal? Our goal is to find this particular point where it is minimum or this particular point where it is maximum and find the maximum height. So only two things we are going to deal with it. So in second example, you'll see this is the maximum height, and clearly this 2 is close to 2, but it is 2 only. 2 is the point of maxima and the maximum height is this height, or maximum height means the value of function. So this height is the maximum value. Corresponding this, most probably it should be 1. Okay, roughly it is 1. And of course in this example this is the minimum, and minimum height is this, and the point of minima is this. Now you must be thinking, what about maxima on this graph and what about maxima on this graph? So it is not mandatory all the time there should be maxima and minima. Graph may have maxima minima, graph may have only maxima, graph may have only minima, or graph may not have even maxima or minima as well. As I told you, this is an application of derivative. So before getting into mathematical part of the problem, I would like to discuss the significance of derivative, but in a very simplistic way. No higher level mathematics, only graphical representation will be there. So I will discuss couple of minutes what is the significance of derivative. You must be wondering, mathematically all of you by this time should be able to differentiate the function, but what is the meaning of differentiation with respect to, I mean, differentiation of any curve given to us. So let us see this with an example. Let me just come over here. Let me consider the function 2 and its graph. This particular function I would like to collect. I may choose, or you may choose any of the function to understand the topic, but I want to use this number 2 function over here. Let me bring it over here. Now you know what is the point of maxima over here. 2 is the point of maxima and this is the maximum height. So let us keep this maxima minima aside. Let us first focus on differentiation of the function. Why I am doing so? Because we are going to use differentiation to find maxima minima. So let us at least try to understand in a very basic and elementary way what is the significance of a derivative. Well, in order to understand that, let me choose one point, that is say 1.5. Now all of you can easily say that 1.5 is not a point of maxima and this is not a maximum height, but we are not interested to find out maxima over here. We want to know what is the differentiation of this particular curve. Now when we talk about differentiation, precisely differentiation at a point. So here let me choose that point be 1.5. So what if I differentiate this curve, that is this function dy dx at x is equal to 1.5? In order to understand that, you have to first consider a tangent. Now if you do not know the definition of tangent, you can pause the video and Google it out and go in detail what is tangent. In short, tangent is a line which passes through the curve touching one point on the curve. So here this green color line is a tangent at this point. Okay. Next, let us consider an angle made by tangent like this. Angle made by tangent and x-axis be say theta. Okay. So there is a tangent at this point and angle made by this angle is this line with x-axis is theta. Then what is dy dx? Then differentiation dy dx is tan of this theta. So tan is some trigonometric function, most of you know already, and theta is this angle. That is, in order to find the differentiation at this point, draw the tangent, measure an angle. The tan value of that theta or that angle is the differentiation value. Okay, like if you choose another point somewhere over here, if you choose another point other than this, like if you choose some other point, like suppose this point, if you choose this particular point, okay, then here you will draw a tangent something like this. Then whatever angle that tangent will make, okay, then corresponding to that angle, tan of that angle is the differentiation value at this particular point. Okay, if you can follow this point, differentiation value at that particular point, okay, and so on. But now what is the meaning of this differentiation? So differentiation will give us information about the inclination of the curve. That is, how much curve is inclined is what differentiation will tell us about. Okay, you see the difference between this particular curve, come to this figure 1, this particular curve and this particular curve. If I ask you at this point, okay, at this point curve is inclined, I mean what I mean is at this point a certain amount of inclination is there in a curve. Suppose at this particular point, okay, you draw a tangent, the tangent will make an angle theta, and at this particular point in this curve it will make certain angle. In which case the curve is more inclined? So definitely you can say the curve is more inclined on this. Okay, curve is more inclined on this. So differentiation is actually responsible for inclination. That is, I'll show you a small example. Suppose you have one curve something like this, and suppose you have another curve which is something like this. Then which curve is more inclined? This is more inclined because tangent to this will make more angle than tangent to this curve. Okay, so this is why we use differentiation. This is the significance, let me tell you, this is the significance of differentiation or derivative. Dy dx equal to tan of theta. Okay, next. Okay, let me consider the fresh one, the same figure over here. Now there is something very interesting when we wish to find the differentiation of the function at the point of maxima. So over here, definitely on this graph, still we are with the number 2 problem. On this graph, the point of maxima is this. Okay, and whatever the tangent, this is the tangent. Now how much angle will this graph make with x-axis? Definitely you can say it will make an angle. Can you guess? It is 0. So if it is 0, then how much is tan of 0? Tan of 0 is 0. Then how much is differentiation over here? Okay, okay. Differentiation over here is this dy dx equal to tan of 0, that is equal to 0. So this is one of the important part of this lecture. At the turning point, when I call turning point, it is definitely the maxima or maybe minima like this. These are our turning point. From here, curve will change the direction. That's why it is turning point. Turning point is either maxima or minima. At the turning point or at the point of maxima or minima, differentiation value is always 0. So let me highlight this, and I want you to keep this as a reminder. Extra note: when the curve is increasing like this, differentiation is always positive. When the curve is decreasing like this, differentiation is always negative. That's why at the turning point it is equal to 0. This is very important note. Whenever you find the curve is ascending, that is if the curve is increasing, then in that case differentiation is 0. Sorry, differentiation is greater than 0. The curve is decreasing, whole on that part, differentiation is negative. And at the point where it changes the direction from positive to up to down, that is the turning point, differentiation is always 0. So let us work on working rule, but before that we need to understand one more very simple and short topic, that is second order derivative. Some of you could easily figure out what is second order derivative. I'll show you with an example how to evaluate second order derivative. First of all, second order derivative means you differentiate the function, you differentiate it again, you'll get the second order derivative. I'll cite few examples. So here is one function, differentiate it, you'll get this. Okay, those who are not okay with differentiation, pause the video, go back to my previous video lecture based on differentiation. You got this when you differentiate, and if you differentiate it again, you will get this. Well, the symbol we use for second order derivative is like this, and if you wish to find third order derivative, you differentiate this again, so you will get 6 over here. So d cube, there it will be d cube y over dx square. But let me restrict myself up to second order derivative. So here is few more example. Sine is there, differentiate, you will get cos. Again differentiate, you will get minus sine. So it is a second order derivative. One more. So here we have, you have a function, differentiate it, you will get this. Differentiate it again, you will get this as a second order derivative. So now let me first make some space over here. So let us now deal with how to find that maxima minima of the function. So here is a working rule for maxima minima. I hope all of you have idea about, if you have a function, you can make a graph out of it, then what is the maxima minima of that function, you will be able to see. Now one more thing is there, you do not have to plot the graph every time to find the maxima minima. That is just to make you aware of what is going on when you solve this maxima minima problem. That is, I wanted to give you some geometrical interpretation of maximum minima, but there is a simple and straightforward working rule to find the value or find the maximum minima and its corresponding maximum value of the function. So here is a working rule. Step 1. Okay, differentiate the function. First case, very easy. Second step, make it equal to 0, because we know that at a maximum or a minimum differentiation is 0. Once you make it equal to 0, solve the problem. You will get an equation, and solve the equation for x. Say I suppose that x1, x2, x3 are the solutions. Now this point are called stationary points. Okay, they have some specific name, they are called stationary points. You may get 1, 2, 3 or maybe more than that, or maybe only 1 point, but let it be in general. Okay, now step 3. Find second order derivative at each point. So you know how to find second order derivative. Find the derivative, second order derivative at x1 and x2, x3 separately. Then check the following condition. If second order derivative is negative, less than 0, function is maximum at the stationary point. If it is greater than 0, it is minimum. If it is equal to 0, we are not going to deal with this case, because this is something special case where function will neither have maxima nor have minima. Well, here let me focus on the main point. This is important and these two are important. So if you remember these 2 points, then you will be able to solve all the problems on maxima minima. So here is one problem I want to solve. So find the local maxima and local minima of the function this, and also find the local maxima and local minimum value of the function. Well, if you remember, this function is same as which I have cited example number 2. So let me bring two conditions that we want to solve the problem. The differentiation is 0 and this is the second conditions to identify whether it is maxima or minima. Okay, let me tell you, first point or first condition is just to find the point where it is either maximum or minimum. Now to precisely know whether it is maxima or minima, you need these two conditions, that is second order derivative. Let me differentiate the function, make it equal to 0, okay, and solve it for x. So definitely you will get it here, x is equal to 2. This is the stationary point, okay. Stationary point will have either maxima or minima. X is equal to 2 is the stationary point. Now we need second order derivative, so differentiate it again. Which function you will differentiate? You will differentiate the first order derivative, okay. So are you getting this? X is equal to 2 is point where it will have either maxima or minima. We do not know whether it is a maxima or minima right now, but we will check using this particular differentiation or this particular steps, okay. So second order derivative, it's -2, straightforward. Now at x is equal to 2, what is the value of this second order differentiation? So value of second order differentiation is not going to change because it is constant, -2, so which is less than 0, which means that the function will attain its maximum value at x is equal to 2. And what is the maximum value? You have to substitute, listen this. Once you knew function is maxima or minima at this stationary point, substitute the value of stationary point in the function over here. That is y of 2 you have to find. Y of 2 will be equal to -2 square and so on. You'll get 1. So 1 is the maximum value. Interesting. This function is not going to exceed 1 as a height. Okay. So okay, let me show you graphically also what does it mean. So graphically this is the function, if you recall that, and obviously 2 is the maximum point. So this is the function which you can see, this particular function is this curve, and 2 is the point of maxima. Okay, don't mix it up. 2 is not the maximum value. 2 is a point on the x-axis where function will attain maximum. So it is a point of maxima, and 1 is the maximum value. So here we finish the problem. Okay, let us consider another example over here. So find the maxima and minima of the function as usual. Okay, the local maxima and local minima of the corresponding function. So let me bring two conditions over here quickly, then differentiate the function, make it equal to 0. You'll get an equation. Well, these are two stationary points. X is equals to -3 and x is equal to +3 are two stationary point. That is, function will either attain maxima or minimum at this point. So what is next? Second order derivative. So find this. Second order derivative is this much. Okay. Then let us first consider x is equal to -2. First let us examine whether x is equal to -3 is maxima or minima. Then what you do? Find second order derivative at this particular point. So over here, second order derivative will turn out -18. That is simply to replace x by -3. You will get -18, which is less than 0, which shows that x is equal to -3 is point of maxima. And you will do the same for another stationary point, because you may get the maximum over here again, or maybe minimum. Let me check. X is equals to, okay, let me first evaluate the maximum value, which is over here. I just forgot. X is equal to -3 is a point where function will attain its maximum. And what is the corresponding maximum value? Just put, as in a previous problem, put the value of -3 in this function. So you will get 57 as the maximum value. Okay. Here is another point, x is equal to +3. And if you wish to find the derivative, second order derivative value at that point, over here like this. So second order derivative turn out to be 18, which shows that +3 is a point of minima. You can refer this, by the way. When derivative is less than 0 at that point, you see, remember, as a whole you cannot conclude whether differentiation is greater than 0 or less than 0 by itself. You have to conclude it at particular point. Only then you will get some number which is negative or positive. Remember this. And in this case we got it positive at +3. So it is point of minima and the minimum value is minus 51. Well, this particular function is also not a new function. I bought it from the previous starting example, which looked like this. You can guess over here what is the point of maxima. Point of maxima is this point 3 and point of minima is this point plus 3. This is minus 3 and plus 3. And this height is what we are talking about. This particular value 57 is this height, maximum height. So you see this corresponding to this, it is somewhere in 57 near to 60 only, right? And this height corresponding minimum height is minus 51, and you can see it over here, it is somewhere minus 51 itself only. That's why I told you, for your information, these graphs are not just a random graph, these are exact representation of the function. But you may not have to do, you are not supposed to draw the graph during solving the problem. This is just to make you visualize what is going on over here. Okay. Over here, this is 3 and this is plus 3 are the maxima point, minima point, this tangent. Okay, you can see this at maxima and at minima, these tangents are parallel to x-axis. Okay, so here we are done with the problem. So now you have to solve few more problems based on this. Well, here are few problems, you can try to solve them.